we're trying to measure force. And you'll be surprised that after today's class, there's actually no devices that can measure force directly. There's no devices. However, we can infer the force by measuring other things. So what are the other things? Things like the strain. Yeah. Out of the strain that we have, we can infer what kind of force. And you may have heard about the load cells. That's also another kind of sensor that we can use to measure force. This basic principle for load cells is also using strain gauge. So you can see a lot of strain gauges being used for measuring force. If you don't like strain gauge, we'll be looking at piezoelectric sensors. We can actually also use that to measure force. Besides piezoelectric sensors, there's also piezoresistive sensors that we'll be looking at. So all these will be the force sensors. And I'll be showing you a video depending on do we have enough time. This tactile sensor where we use touch for sensing. We want touch for sensing. Particularly, it's also running on the basic principle of piezoelectric transducer, piezoresistive transducers again, for sensing touch. And even ultrasound can be used for sensing touch. So that touch part, you can imagine that how we're going to get a force feedback in order not to crush a thing that we want to hold with. And the light sensors, that's the next topic. We'll look at a few types of light sensors. I know a lot of you have been using piezoresistors, but there are actually more than one type. In fact, there are three types. There's photodiodes, there's phototransistors, photoresistors. So I'll be outlining to you like how do you go about choosing among the three of that. And we'll wrap up this tactile sensor based on light, using light. Particularly looking at the optic fiber. So that's what we'll be doing today. All right. So the force sensor is one type of external sensor because if you want to measure force, for example, the end effector, which is the robotic arm, the end effector is going to move and strike something at certain force. So you will have an external sensor to measure that amount of force. External sensors usually deal with the overall task control. So your robot, if you want to have some sense of controlling, then you need most of the time to have some force sensors or feedback. Right? You can send signal to say how much it wants to move at certain velocity, acceleration. Those are your internal sensors. So the external ones usually will be used for the overall task control, and it provides the feedback. Like I was saying, force cannot be measured directly. We estimate it through some of the other mechanical properties. For example, elasticity. You'll be looking at two types. One would be the strain gauge, and the other one is the load cell. Let's have a look at the strain gauge. Now, strain gauge, obviously, you need to start by understanding the definition, strain. So, if something is under strain, what that means is that originally you will have this length L, and you apply force to it, and that thing would deform to have a little bit change of that L. So you could imagine it like a rod. So you apply force to that. So originally it has length of L, and if you apply force on two sides, this is going to extend a little bit more. We call that a little bit more delta L. So if you take that ratio, delta L, divide by L, then we call that strain. If you look at the units, what is the unit of strain? Is there a unit for strain? What do you think? No. Yeah, it's dimensionless because the change in length in whatever units, like meters, divided by length, which is also meters. So there's no units for strain. There's one thing about this phenomena that we could exploit. So engineers goes about trying to look at some phenomena and then we try to exploit. One of which is the resistance. So we discovered that if we were to pull that strand of wire, because you can imagine this volume is going to be fixed here. After pulling it, you have a little bit of delta L over here, but something tells you that the diameter is going to shrink here because it has the same amount of material, same volume. If you stretch it, still the same volume. Why is it longer? That's because it has become thinner. Right? So this is what is going to happen. Whenever you stretch something, if it elongates, then its cross-sectional area is going to shrink. Right? We're going to exploit this property. How are we going to do that? We know that for any kind of conductor, there's always some level of resistance. If you apply current through it, then this conductor would have some amount of resistance. So if I were to stretch that wire, its resistance is going to change. And that amount of resistance that will change relates to this equation over here. So those words are just trying to say this equation. And actually, Glasgow didn't write this equation, he just wrote down the words, so I thought it would be good to include that equation for you. Now, don't mistaken that this rho is density. No, it's not talking about density. It's actually a constant of proportionality, or we always call it the resistivity. So resistivity, rho is resistivity. It has the unit of ohm meter, right? Not ohm per meter, it's ohm meter. So now if I were to ask you, okay, you're gonna have that strand of wire, I'm gonna stretch it, pull it, and you know that the cross-sectional area is going to drop. How about resistance? If cross-sectional area is going to drop, what happened to its resistance? Its resistance is going to increase. All right, that's looking at the equation, but you will want to understand what's going on over there. Why is it that when you stretch it, this cross-sectional area shrinks, and then the resistance would increase? If you could imagine that in order for current to flow, we were saying that any strand of wire, there's certain amount of resistance. So this current is trying to flow through these atoms that's trying to block it here. So there's a resistance. So it couldn't really flow very well. Now imagine if you squash all this cross-sectional area, where all these atoms are going to get closer to each other, you're going to experience more resistance. Right? So hence, the resistivity will increase. So if you stretch something, then its resistance value will increase. So how about the other way around? Let's say if I were to decrease the length of this. So if you look at this equation, L at the numerator, if you were to decrease that, what happened to your resistivity? Your resistivity would also decrease proportionally. So we can play with these two values, the length or the area. And we can exploit this property in order to help us to sense indirectly how much is the force that's applied to our system. So we can infer that. So in order to know how much change in the resistance we can expect from various metallic materials. You would know that for different materials there will be different resistivity. But then the amount that you stretch it for different materials, respectively, the amount of change in the resistance would be different for different materials. So if I stretch copper, its resistance is going to increase, but that amount of increment is going to be different if I were to use an aluminum wire and stretch it. So then, what is that governing equation? That one is given by this. I thought maybe I'll just elaborate a little bit more on this. So I'll move on to the slide. So you can just write down a little bit of these notes. How do we get to that form here? Because it may be hard to just purely memorize things. So I'm going to make use of this figure over here. We're going to start with that equation, R rho L over A. So what I'm going to do is to multiply L at the top and the bottom, essentially not doing anything much to it. But why am I doing that is because later on I want to make use of certain relationship. So if I do this, then the numerator will be rho L squared over denominator, that's AL. Now, area times length of that wire, what does that give you? That gives you volume. So I'm going to write down volume over there, V. So V, volume, is volume. And not only is a volume, particularly we know that it is going to be a constant value. Right? Because when you stretch that strand of wire, its volume will not change because that's the amount of material that's in there. You can stretch, it can elongate, but its volume is still going to be the same. So with this, I can differentiate this R equal to rho L squared over V. Differentiate this relationship. So dr dl differentiate with respect to L, since V now is a constant. Yeah. So I get 2 rho L divided by V. Okay, just differentiate that one. And what I'm going to do next is to multiply L at the top and at the bottom. Okay, so that will give me 2 rho L squared divided by LV. So this part over here starts to look familiar, all right? So that's actually 2R over L. Why is that so? Because we were defining it. R is equal to rho L squared over V. So we can replace that part by R. So the next step I want to do, the R over the L now is equal to 2R over L. In mathematics, we could use variables, separables. Do you know that? Maybe you know it if I were to write down. I can put this dr and then bring that r on the right hand side down, equal to 2 dl over L. Yeah, variable, separable. So why I do this is because I'm interested to look at for small change in length, L, and resistance, R. For small change, that means I want a delta instead of del. Delta R over R equal to 2 delta L over L. So this is a relationship. This number over here, this is what we call the gauge factor. So the gauge factor is actually our constant of proportionality. Right? Or sometimes just GF. Yeah? GF, that's this gauge factor. So in a lot of various different materials, the gauge factor is given by a constant that's called K, right? Because for different materials, its gauge factor is going to be different. So generally, we could write delta R over R equal to K delta L over L. And we know that delta L over L is actually our strain, epsilon strain. So this is how that notes got to this form. I want to extrapolate a little bit. This gauge factor, if you look at it, I could bring this part here to the left-hand side, and I'll get delta R over R divided by delta L over L. Now what this means is that gauge factor is the relative change in resistance divided by relative change in length. I want you to take a look at that relative change in resistance divided by relative change in length. This relates to the material. If I have a gauge factor that's high, it tells me something about this material in terms of if I were to pull it and then its resistance would increase by how much, that's governed by the gauge factor. So if the gauge factor is large, what does that mean? It means you actually don't have to apply a lot of force before you get quite a good reading in the change of your resistance. That's what this thing is saying. Right? If the gauge factor is large, that means you get a lot of readings over here with very little change in your length. So this is good for us because our job at the end of the day is still measuring force. Yeah? So if I have something that has a very high gauge factor, I just need to apply a little bit of force and I get a lot of change in resistance. That's good output for me. That's a good result. This is just like sensitivity, if you remember our topic, sensitivity. Very little input and you get a lot of output. That's very sensitive device. So for various different materials, there will be various different sensitivity value. Or in our case, this sensitivity relates to resistance with respect to the change of the length. So we call that the gauge factor. So the next slide tells you about this list of materials. So you could see a lot of materials over here. Actually for strain gauges, that's what they are using for those materials. Particularly, you could see the best one down on this table is semiconductor. So does that sound like, okay, all strain gauges henceforth will be using semiconductor to construct it because that one is going to give us such a good gauge factor? You'll find that most of the time, no. A few reasons. Semiconductor is expensive. Semiconductor is susceptible to the change in temperature. So if there's a small little change in temperature, your semiconductor, even though there's no force applied to it, you get some reading. So that's not good. It doesn't really help us. But there are certain cases where we would use semiconductor. If let's say if it's a thermally insulated environment. Now, the strain gauge, I'm not sure, have you seen before how strain gauges are attached to a beam so as to measure the amount of strain, and we'll be using that to decide the amount of force that's applied to it. Normally it's glued onto your structure, and the amount of glue is not like a Scotch tape glue where you have a strain gauge over here and your beam is over here and you just glue to that. It's not done that way. It's applying glue all over it. You're concealing the entire strain gauge in this bubble of glue. That's because strain gauge is a very sensitive device and it needs to be really solidly stuck onto your structure so as to experience every small little bit of strain, right? So once you apply strain gauge to your structure, gluing it there, you can't remove it anymore, right? So because it's completely glued in there. There are a lot of there's some other materials that's made from germanium. Usually you find the silicon type, and they dope it with a small amount of impurities so as to increase the sensitivity. There is a prototype that I made. Maybe I'll switch to that visualizer. Okay, I want you to make a guess. This is my small little model of strain gauge. In fact, I made a photocopy of that picture that you have, and then I cut it out, and then I put it on this sponge. Why do I put it on the sponge? Because I want you to think about this. After listening to this concept, the strain gauge, if you were to buy this and apply it to a beam that's flexing in this way, flexing in this way, you think you put this strain gauge in this manner or that manner? Right? It's flexing in this way, this beam. Right? Think about this concept. You put your strain gauge in this manner or this manner. A or B? A, B, B. There are some B's. Can the A talk to the B? Why you choose A or why you choose B? Yeah. Okay. So if this strain gauge were to flex, were to be placed in this way, it's gonna flex this way, right? Yes. So the beam is here. If you place it over here instead of this way, over here, then it's gonna flex this way. Yeah. If you put it in this position, if the beam were to flex up and down in that way, that means this strain gauge would flex in that way. Yeah. So it's either you want it to flex this way or flex that way. So if you were to flex this way, what's going to happen is that this crisscross line is going to get further away from each other. But we're after measuring the force using the concept of resistivity. The concept of resistivity relates to the change in that cross-sectional area of each one of these strands. In order to change the cross-sectional area of this strand, which direction should you be pulling it? You'll be pulling it this way, so that you can experience that strain in all of these strands over here. Yeah. So that's how you apply the strain gauge. So you know, just tell a chief engineer, yeah, you learn it from Dr. Tan today. This way, not that way. This way, you don't get any much reading. Only that. There's also one other interesting thing. Did you ever notice that the strain gauge seems to have this part here, and then it goes like a little bit thicker, and then thin, thicker, thin, that way. Now this part obviously is for you to do your soldering. Solder to that strain gauge so that you could read the change in that resistance. Now this material is not copper. Yeah?
that list of materials that you've seen just now. But what is interesting is that why don't they exploit this part here to be the same thickness as that one? Why is it that it's broader over here? It has to maintain that structure, and actually most of your strain data is not coming from this thicker part, because this wider part. This wider part, actually, when you flex it, its cross-sectional area is not going to change that much. Most of it is going to come from all these narrower strands. So narrow strands, when you stretch, when you apply a force to it, then there's more appreciable change in your cross-sectional area. That's why it's designed that way. It's kind of like the skeletal form to hold it together. But the whole thing will be glued down to your structure.
Okay, so that's how it looks like. So the sensitivity direction is along this direction. This is a transverse direction, but it doesn't read much data. So you want to maximize the x direction. In this case, x direction is in this direction. This one shows the construction of your strain gauge. How is it made, especially for the semiconductor strain gauges. I was talking about it's very susceptible to temperature, so highly temperature sensitive, and also semiconductor material is pretty brittle. And what that means is that if you were to use that, the amount of strain that you can experience is not really that much, even though it's very sensitive. So you got to play with that. Do you want more sensitive strain gauge, or do you want something that can experience a larger amount of strain? And also, semiconductor material is not linear. So you've learned in the first lesson about nonlinearity. There are some ways to do the correction, but usually if you do correction to something that measures non-linearly, that means you need to have enough circuitry to do the compensation. So overall, your sensor will become more expensive. So that's why it's written here, more expensive. So the semiconductor strain gauge offers actually another dimension. We can actually use it as a sensor device where it can incorporate some form of signal processing or communication circuitry. What it means is that besides able to sense the change in resistivity, it provides this communication possibility. Later on, you get to see what do I mean by communication possibility. You can actually apply strain gauges to tell you about the health conditions of certain structure. So it's able to help you to monitor not only the force, but to able to tell you the health condition of that certain structure. So at the end of the this lecture, there's some information about that. Now this change in the sensitivity to temperature, oftentimes your strain gauge that you buy, it usually comes with a temperature compensation circuit. So the temperature compensation circuitry would not be covered in this module. Instead, we want to relate the input voltage that you apply to the circuitry of a strain gauge, and then relate that to the output. So in this set of notes, it just gave you this set of equations, but I want to walk you through in pretty much of a one-page detail how to get to this form. The strain gauges, normally they are arranged in a Wheatstone bridge. Wheatstone bridge is a structure that looks like that. So you have this part here, I think I write down. This one has a resistance that we call A, resistance that we call D, this one is B, and resistance that we call C. So this is where you supply the voltage, and immediately in your mind you should be thinking, this sensor requires power input. You need to supply power. So this is the part over here. You need to supply power. There are other sensors that actually do not need you to supply power because itself is power generating. An example, piezoelectric material. So later on we'll have a look at that. So this one requires the power. And the way it's arranged over here is in this very strange structure. We call it the wisdom bridge. The output, we tap it out from over this side. I'm going to resketch this one so that it's easier to see. So we have this 4 resistors. So there are 4 resistors over here, RA, RD, RB, and RC. And the voltage supply is plus minus. It's connected over here. And you have this end that's tapped out in the following way. And this is our output voltage, this is our input source supply voltage. And we're going to try to solve this circuit. So we're going to use this principle that's called Kirchhoff's voltage law. Sometimes this is pronounced in a German way, Kirchhoff. But yeah, if you don't speak German like me, you can pronounce it as Kirchhoff. So this law says that we can break down these circuits by having this Kirchhoff voltage loop. Here, I'll write it down. Kirchhoff voltage loop, KVL, using the KVL principle. So the KVL says that summing up all the voltages in a loop will equal to 0. That's the Kirchhoff's law. So I'm going to use different colors to represent that. So the first one, let's say red color. This one, the way the current flows all the way back to the source in this direction, we call it loop 1. Later on, there'll be another loop that goes along here and over there before coming back again. This one we call it loop 2. And there's one more loop, green color, that goes from here through here and then back in this way. This one I call it loop 3. So 3 colors so that you could see them very easily. I'm going to start with loop 1, right? Loop 1. So KVL says that the algebraic sum of voltages in each of this loop is equal to 0. So I'll start with loop 1, the red color one. So that one starts with Vs plus, maybe I forgot to write, the direction of the current in this distribution. This one here, we call it IA. This one we call it IB. We don't know what are those values yet. Maybe it's easier to use 1 or 2. Okay, let's call this as I1, and that one is I2. so that it's easier to differentiate. So I1 will also flow through in that way. This one I1, and over here will come up here I2. Now these are assumed direction, yeah, for the other I1 and I2. If it's the opposite way, then if you work it out, you still come back to the same answer. I'm going to assume that I1 flows from here up there in that way, and I2 would flow in that way. Okay. So with that assumption, I would know that there's this sum of your voltages across these two resistors. So that will be RB plus RC I2, right? Because I'm referring to loop 1, right? So this, all of the sum of the voltages must be equal to 0. So I2, now I can re-express it, is equal to minus Vs over RB plus RC. I can't scroll up and down, so you can refer to that sketch in what you have written down. I'm going to go to loop 2. So using KVL, loop 2. So in loop 2, is that green, is that blue line over there? So loop 2, it would also go through your Vs plus the other two voltages from resistor A and D. So RA plus RD multiplied by I1 equal to 0. Right? Because voltage is resistor multiplied by resistance multiplied by your current. So those are the two voltages. And I can express I1 in the following form: RA plus RD. And the last loop, using KVL again for loop 3. So loop 3 would be that green one. So if you could refer to that. So for loop 3, there will be your output voltage V0 minus, in this case, okay, I'm just going to quickly scroll up. If you loop it in this direction, this one will be positive, that one will be negative because it's against the direction of the current. So the voltage for this will be a negative value, so it will be minus RD I1. So I'll be writing that down, minus RD I1. And the other one will be positive direction, so plus RC I2. All of them summed together is equal to 0. So I can substitute I1 and I2. So V0 plus RD Vs over RA plus RD, because I have I1 expression over there. There's a minus sign, so it became positive here. And this one will be minus RC Vs over RB plus RC equal to 0. So let's do a little bit of simplification. There's a common factor Vs that I can bring out. So I'm going to bring these two terms to the right hand side. So I have RC over RB plus RC minus RC over RB plus RC Vs. Okay. So now, what I'm going to do next is that after this expression, I'm going to replace RA, that resistance RA is replaced by an active strain gauge. So all those resistors that you can see, RA, RB, RC, RD, they are fixed resistors, yeah? So what I'm going to do next is just to replace that RA fixed resistor with a strain gauge. And I call this strain gauge with a resistance RG. And then the induced strain by that RG, if there were to be any strain as a result of that, I'll get a change in that resistance, delta RG. a small change in that resistance, delta Rg. So well, actually you can just write delta R. So I'll just write delta R. A small little change in that resistance delta R for that induced strain. So this is going to be giving you delta R over Rg, and that will give us our gauge factor multiplied by the strain, the formula that we saw just now. So what we're going to do next is to assume Rb is equal to Rc, so we can set these two resistances to be the same, and Rd is equal to Rg. So Rg will start with a certain amount of resistance, and we're going to match that resistance with Rd. All right? But Rd is not a strain gauge, and it is not a strain gauge. It's Rg that's the strain gauge. So if we equate in that way, then when Rg is flexed, when we flex it, then your Ra now will become Rg plus delta R. Okay. So once we have that, since your Rb is equal to Rc, so this term over there, I'm going to bring this down, would become the following way. So this would be Rc divided by 2Rc, right? Since Rb is equal to Rc. So that will give me half. Minus Rc over Rb plus Rc. Okay. It's Rd, is it? I wrote it 2 times. Yeah, this one is Rd. This is Ra, and this is Rd. I wrote it 2 times because I brought it over and copied the same thing 2 times. Okay, this should be Rd. This one is A. So over here, my Rd, I was saying that I will change it to Rg. So you'll be divided by Rg plus delta R plus Rg. Because I was saying that my Rd is equal to Rg, right? So that's how I got that, and multiplied by Vs. So this one can be simplified, equal to half minus Rg, and if I were to take away this round bracket, I'll get 2Rg plus delta R multiplied by Vs. So I could bring out that common factor of half Vs. So whatever that's left will be 1 minus 2Rg over 2Rg plus delta R. So if I were to take the common denominator, I get 2Rg plus delta R minus 2Rg divided by 2Rg plus delta R. So this and that could cancel off, and I'm left with half Vs delta R over 2Rg plus delta R. So that was given to you in your set of notes, right? This final form. So if delta R is small, And in most cases, delta R is just going to be very small compared to your RG, just a little bit of a change in resistance. If that's the case, then this term over here, delta R, because it's 2RG, if this RG is very big and this is very small, we can say that your V naught is essentially equal to delta R over here divided by 2RG. Right? So this term here would be a lot more smaller compared to your RG. So we can simplify it in that way. So hence, you have Vs multiplied by delta R over 4RG. So that's the next set of equation that was provided. And I want to include a little bit more of information. This expression over here, V naught over Vs, is equal to delta R over 4RG. Did you see if V naught over Vs, what's the meaning of that? Transfer function. So what I've done over here is to find out what's the transfer function of a strain gauge by relating the input to the output. Okay. So that one, the output divided by the input, you get this expression. This expression is the transfer function of your strain gauge. So you could use the transfer function of your strain gauge in your control system. So this is your transfer function. So there are a few types of, a few ways of planting your strain gauge. I'm going to reduce it. If you have a cantilever, normally you could put the strain gauge at the top and the bottom of your cantilever where you will experience the strain. So when the cantilever is being deformed, your strain gauges would also respectively experience that change in the resistance. So this sort of arrangement on a cantilever usually is to use to measure the tip displacement between 1 to 30 millimeters. So if your tip of the cantilever is experiencing more than 30 millimeters, then a strain gauge is actually not suitable, because then you will experience too much strain on the strain gauge. The strain gauge on a cantilever, being it's a structure that deforms almost like a circular way, right? For a cantilever, it's not a linearly translational motion, but it's pivoted and extending in that way. Because of that, you experience a little bit of nonlinearity in your strain gauge, up to an order of about plus minus 1%. Another way is to, so the one that I was talking is this, right? This figure for a strain gauge. Another way is to use it on a manipulator, or sometimes we just call it the end effector. So for every end effector, there's actually a wrist over there, this kind of device, to allow your end effector, that gripper, this part is called your gripper, to allow the gripper to rotate. So as it rotates, you want to understand the object that is carrying, how much strain it's experiencing. So we'll put strain gauges along, embedded inside the wrist. Particularly, you put it, I'm going to zoom in so you can see. Yeah. So you're going to put the strain gauge along this way, and that is for your moment along your y-axis, right? To be able to sense that kind of strain. And for this axis over here, for your z-axis, you're going to put the strain gauge over here in that way at the top part. And for your y-axis, you're going to put it in this way. All right? So putting it in those few ways allows you to measure your x, y, z axis, the strain values, so that you would know what is your end effector wrist, what kind of forces it's experiencing. Now, since strain gauge is a sensitive device and you can't really use it to measure tremendous amount of force, there's another way that you can use it to help you to measure larger amount of force. That is put it into this cylindrical drum over here. So this drum is actually not a solid structure, but it's kind of like a tube structure. So this drum over here, in there is empty. It's just like a pipe, a cylindrical tube. And as you apply the amount of force, you could imagine that this part here is going to bulge out. So as it bulges out, you will experience the amount of strain. So these strain gauges are positioned in that following way to capture all the strain characteristic of how this cylindrical tube is deforming. And given that it's a tube structure, it can take in a lot of force, typically 50 kilonewtons to 10 meganewtons kind of force. So that's seriously a lot of force. And this kind of sensor device, we can call it the load cell over here. Right? We call it the load cell. Usually this structure is more suitable for compressive force. Yeah? So if you have extensive force, this can be used as well, but to a more limited range compared to your compressive force. We don't need to touch on the temperature compensation, but you could see that for strain gauge, given that it's very thin and very small, it's very susceptible to change in temperature. So that's actually a thermal circuitry for compensation. But I noticed that it's not really covered in your module. If I'm not wrong, last year I asked your senior, they said it was covered somewhere else. Temperature compensation for strain gauge. You have another module that talks about that? No, maybe not this year, but that's what your senior said last year. And because of that temperature compensation, we need to have certain signal conditioning circuit. So it's not just placing the strain gauge in the weak